To look at the naming for this one, you want to recognize there's two nitro groups and an alcohol. A benzene with an alcohol is a phenol group. And the alcohol is at carbon 1, so we number from there. Get 1 for dinitrophenol. In the second example, we have ethyls and isopropyl groups. Neither of those have special parent names. This will just be benzene. And we can number it 1, 2, 3, 4. And I can try numbering it a different way. The goal is to have lowest overall numbering. If I go in the blue direction, I have 1, 2, 4. In the red direction, it's 1, 2, 5. So I'm going to go with the blue direction. So my name will be 2-ethyl. That comes first alphabetically before isopropyl. And then I have 1 for diisopropyl. Benzene. To draw anisole, anisole has a benzene ring with a methoxy group, or OCH3. Chloro is at the 4 position, and at 2 and 6, I have bromine. To predict whether each of these things are aromatic, we have, it has to be cyclic, conjugated, have 4n plus 2 pi electrons. So if I add up the number of electrons here, this is cyclic, it is conjugated. We have alternating double bonds and single bonds. I have 2, 4, 6, 8, 10, 12, 14 pi electrons. So it'd be 4n plus 2 equals 14. So if n equals a whole number, this is aromatic. In the second structure, we have it cyclic and conjugated, and we can look at the number of electrons. There's 16. N is not a whole number here. So this is not aromatic, but we can look to see if it's anti-aromatic, which would be 4n equals 16. So this is anti-aromatic. And then here we're looking to see if the lone pairs are participating in aromaticity. So remember, for aromaticity, we need it to have conjugated double bonds, or conjugated pi bonds. It has to be cyclic and has to have that 4n plus 2. So in A, the oxygen has lone pairs that it can contribute to the aromaticity, and so it actually will. So one of those electron pi bonds, or one of those pi electrons, will be part of that. So this one does. For F, we have nitrogen, which also has lone pairs, but nitrogen in both situations here in the ring are part of the double bond. So this is sp2, so these ones do not participate in the aromaticity. And for G, again, we have one of these here that participates. So this is a yes. All right, so we're going to change gears and do an efficient synthesis. So what I'm noticing is that I've added an alcohol. That's the only thing that's different here. So we can look at our reactions where we can add an alcohol or some functional group to the benzylic position. So I can use NBS. And that will give me a BR here. You might be tempted to use NaOH to make that OH there. However, we have a benzylic and tertiary position, or we can't do SN2 here, so no SN2. But we can do an SN1, so we can just add H2O with catalytic acid to get to that compound. All right, on this one, we are adding, again, you want to observe that this is the benzylic position. So maybe my retrosynthesis look like some Br there before there was an OH. So I can think about putting a Br at that position, which we can do with MBS. That one is still tertiary, so I don't want to do an SN2 there, but I can think about doing an SN1 with methanol, H+. So in this one we have that benzylic carbocation that can form, which is very stable. And then my nucleophile is methanol, which can attack there to give us that product. So this is our intermediate. And methanol is free to attack that carbocation. All right, here we are adding carbons to the end, and then we also have an OH there. So I've added 2 carbons, and it's 2 carbons and an O away from there. So I'm thinking of an epoxide. That I can use to attack those 2 carbons that are there, and I have a Grignard that I could attack with the epoxide. So to get to the epoxide, I can go through the alkene, and I would just need a benzylic leaving group. So in the forward direction, NBS. I'm going to do an elimination with any base. There's only one beta proton there. Make my epoxide. Then I can use ethyl Grignard, followed by water to get to that epoxide. So it's going to do a ring opening at the less substituted position. And open that up to the alcohol. All right, in this reaction we're looking at products when it's under Birch conditions. So that's going to give us a cyclohexadiene. When you have these 2 R groups on here, these are both considered electron donating. And the electrons want to be, or the pi bonds want to be on the carbons with the electron donating groups. So you want to try to accommodate both as possible. And this one does just that. So you could have that, or this right there. So those would be either situation. In a case where your groups don't exactly line up, you still try to make them both happy. And you can do it that way. So you have your cyclohexadiene, both parties are happy. So the electron donating groups want that pi bond, electron withdrawing groups don't. All right, which of these are aromatic? So we're looking for 4m plus 2 or odd number of pi electrons or pi bonds. Double bonds. And one of the things you can do is think of benzene. I know that benzene is aromatic, so I look at those things to remember. So benzene has 3 double bonds, which is an odd number. This one's aromatic. These 2 rings have 1, 2, 3, 4, 5 double bonds. This one is aromatic. That would be 4n plus 2 equals 10 pi electrons, and that would come out correctly as well. For D, it's cyclic. It is not conjugated all the way. This one is sp3, so this is not aromatic. All right, here we're looking to see if it's aromatic, non-aromatic, or anti-aromatic. In this first structure here, we have 2, 4, 6 pi electrons plus this lone pair, which is participating. So there's 8 pi electrons. 4n plus 2 equals 8. So this one is not aromatic, but we can test to see if it's anti-aromatic. N equals, 2. So this one is anti-aromatic. E, let's go to C. So C, it's cyclic, it's conjugated. Sulfur has a lone pair that can participate in the aromaticity. So there would be 2, 4, 6, and 4n plus 2 equals 6. That works out, so this one is aromatic. And then E, the lone pair is contributing to H, but when nitrogen is involved, the double bond, it doesn't need the lone pair, so this one is aromatic. It has 3 double bonds. And for F, that oxygen, there's an oxygen lone pair that is contributing to the H, but you also have a second one here, and that one can be part of the structure, so this is aromatic. All right, predicting products here. This is one of the problems in the book that for some reason didn't get numbered, so it's an unnumbered problem. NBS is going to brominate at the benzylic position. Sodium dichromate is going to oxidize benzylic hydrogens, and we get benzoic acid. So even though it's secondary, all of that stuff gets cut off. We just end up with benzoic acid. If we add acid and heat, the sulfuric acid is going to protonate that alcohol to make it water, which is a good leaving group, which will leave. We get a benzylic carbocation, which can then undergo an elimination. And then with sodium ethoxide, we'll probably get a mixture of products here. Can get the SN2 plus the elimination. Right here we're looking at syntheses. We have a bromine, and then we're adding 2 carbons here. So we can't do any attacks at this carbon because it's sp2. So we need to use this as our nucleophile. So we can use Grignard there. And then we have to figure out what we want to attack. So there's a couple of different things that you could do, but we need to add 2 carbons, and we also need to have a double bond at the end. So if I make this into a Grignard, you could attack an epoxide if you wanted. Convert that to a good leaving group. And then do an elimination. So that is one thing that you could do. You could attack ethyl bromide. So you get the ethane there. Put NBS to make a leaving group at the benzylic position. And then do an elimination. You could attack an formaldehyde, or I guess acetaldehyde. So that would give me my alcohol at the benzylic position. Use zinc chloride. And then do an elimination. So there's a couple of different options for you to do that one. All right, here I am having a chloride at the benzylic position now. This is HCl. I don't think this was a synthesis problem. It might be a mechanism question, since there's a reagent there. So if we were doing a mechanism, we have a proton transfer. We're going to get loss of leaving group. That water is going to leave. We have minus H2O. I'm going to form that carbocation. If I go next door, that's a benzylic carbon, which is more stable than tertiary. So that's going to shift over there. The hydrogen will. So I'll have the benzylic carbocation. So that was a rearrangement. And then the Cl minus can attack there. All right, some more synthesis problems. All right, here we are not adding any carbons. We are moving the alcohol from one group to another. So we can just make that a better leaving group. Maybe I feel like tosylating today. T-butoxide. And then here I need 9 BBN or BH3. And H2O2. And this last one here, I'm adding an alkyne. That makes me think of adding it to this, which we can do very easily using NBS. And then I can take acetylene, then I attack that benzylic carbon, and we get the target molecule. All right, and those are the chapter 18 extra problems.